Okay, we got back to chapter 3 and really the nomenclature part last time. So kind of chapter 3 nomenclature. And we started talking about ionic sort of naming. And remember, as we talked about, if you do have ions, which can be obviously a cation, which is positively charged, or an anion, which is negatively charged. If you are writing the formulas for either of these things, you do need to make sure that you do include the charges. So if we had something like K plus or Ca2 plus, we do want to make sure if we're asked to write the formula for an ion, it is not an ion if it doesn't have a charge. So it does need to make sure it does have the charge. Or if we have a negative one, O2 minus or Cl minus. Now, when we name just ions by themselves, pretty much positive ions or cations are really just a whole name of the element. So potassium, then we just put ion at the end, or this would be the calcium ion. It's the nonmetals that really have sort of the change in the name, and the change is basically IDE at the end of it. So we drop some of the last part of the name, or sometimes even more. Here, this would be the oxide ion. Instead of chlorine, this would be the chloride ion. And as we talked about, whenever we do put, again, a positive ion and a negative ion together, like calcium and chloride, we do want to make sure that the overall charge is equal to 0. So again, we would need 2 of those guys to give us CaCl2 as the proper formula. When we write a formula for an ionic compound, there should be no charges included, but it is made up, obviously, of things that do have charges. And by the way, the anion for chloride is Cl minus, not Cl2 minus. That is not right. So again, the 2 means you have 2 of the Cl minus ions that are present. To name an ionic compound, we talked about type 1 compounds, and type 1s are ionic. And again, with an ionic, you always have a metal and a nonmetal. And as I talked about last time, pretty much if a metal is involved, that's really what's going to determine how you name something. That's always what you want to look at in terms of how you should name this particular compound. And in the case of a type 1 metal, that means that it has a fixed positive charge. And usually what that means is from group 1, 2, 3 are zinc, cadmium, or silver. These are all metals that have fixed positive charges. And because of that, you really just roll with the whole name of the metal. And the non-metal, again, gets the IDE treatment at the end. So here, this would be calcium and chloride. Remember as well, we do not have to worry about extra of each of those things in terms of the name. We definitely never ever use a prefix when a metal is involved. So if you have a metal, that's again a good way to remember, should you use a prefix or not, and you definitely should not. So no prefixes when metals are involved. They have their specific place, which we'll get to obviously next, or as we continue on. Any questions on any of that there? All right, then let's continue on. We're going to talk about type 2 compounds. And type 2 compounds are also going to be ionic, and they're also a metal and a non-metal together. So the difference here is the metal. And as I mentioned before, that metal is the most important thing. And here it is a metal that is pretty much going to have a variable positive charge. And that is, for the most part, going to be your transition metals, are just to the right underneath the staircase in the area where you find like lead and tin, etc. Again, even though those guys are not technically transition metals, they are really named the same way. So when we come across, obviously, a transition metal, except for those 3 that we just talked about, the zinc, cadmium, or silver, it is a type 2 metal. And the way that we name type 2 metals is very similar to the way we name type 1 metals. We still use the whole name of the metal. We still roll with the non-metal getting the IDE treatment at the end. But the additional thing that we include on our type 2 sort of compounds is we include a Roman numeral. And a Roman numeral is the actual positive charge on one of the cations, not the total charge. It is not where a lot of people mistakenly think how many metals you have. It is if you took one of the metal charges, one of the metal ions out, what the positive charge is. So for example, if we had FeCl3, we would look at this and go through our sort of normal things. That is a metal, and obviously that is a non-metal. And again, that should check off the ionic box. We then want to focus in on the metal, and the metal is a type 2 metal because it's definitely dead center of the transition metal region there, and that should definitely tell you it has a variable type of charge. So we want to figure out what the charge is on the iron in this case. The good news is you will always know the charge of whatever it's attached to. So whatever it's attached to, you'll definitely know the charge of. So in this case, we basically got one iron, and we got one chloride, two chlorides, and three chlorides, basically, is what that means. That means we add up all the negative charge. We got basically a -3 happening there from each of the chlorides total. And that means because we only have one iron, our iron in this case must be carrying a +3 charge to balance it out to 0, right? So it's still an ionic compound. It needs to equal 0 when it's all said and done. So that's really all we need to figure out in this case. And now we're ready to name it. Iron, it would be Roman numeral 3, again, because of the charge on the metal. And once again, no prefix here. It doesn't matter how many of those Cl's we have. It is just chloride in this case. So iron Roman numeral 3, chloride would be the name here. Again, the additional thing you have to do is figure out what the charge is on the metal, but you could always figure it out based on what it is attached to. Any question? Now, why do we need the Roman numerals? Well, we need the Roman numerals, for example, let's just say we have this guy, FeCl2. And in this case, same idea. We have metal, non-metal, which tells us it's ionic. We have iron, which tells us it's a type 2. So same idea. We have an iron in this case, but we have not 3 chlorides in this case, but we actually only have 2, which is a -2. That means that the iron there is going to be carrying a +2 charge in this case. And that means that the name of this guy would be iron Roman numeral 2, again for the charge, and again chloride in this case. So with type 2 compounds and type 2 metals, because they can make multiple types of positive charges, you basically need to tell everybody, thank you. You need to tell everybody what the charge is in this particular case. The first one, we're saying, hey, we're doing the iron with the +3 charge. And the second one, we're doing the iron with a +2 charge. The reason you don't need the Roman numerals on a type 1 is they can only form one type of charge. So sodium will only be +1. It'll never be anything else. So you don't need to tell people, hey, it's going to be +1, because it should never be anything other than that. So on these ones that have variable charges, you do need to use a Roman numeral, basically to tell everybody this is the charge on that one to begin with. Any questions on that one there? So again, here is our transition metals. The 3 exceptions, obviously, there are type 1 transition metals are going to be those guys there, but everybody else in there is going to have it. And again, also in this region, just outside of it, will deal with multiple charges. Now, that really did not work very well, that one did. So let's take a look at what's not really here. We will use the Roman numerals here to indicate our charge on our variable metal. There is an older school name, which is, all scribbled over here. I think you have this in your book, kind of on top of each other, where they actually don't use Roman numerals, and they use ic or us as the ending. Ic is the larger positive charge, and OUS is the smaller positive charge. And they also use more of a old school type name. So for example, copper 1 would be cuprous. Copper 2 would be cupric. Iron would be, iron 2 it is there, would be ferrous, and iron 3 would be ferric. And they kind of use that kind of older school names. We will not use those, but sometimes those names do still pop up, especially with copper and iron. Very commonly, people use ferric, ferrous, cupric, cuprous for copper and iron. So they still sort of pop up, but we will explicitly use Roman numerals. And one of the weird ones for our type 2 is mercury. So we have mercury like this, and we got mercury like this. And oddly speaking, the one with all the 2s is actually mercury 1. And the one with just 1 2 here is mercury 2. And that's because mercury 1 comes as a dimer. It's basically 2 mercury 1s stuck together, which is why the 2's on the bottom. And plus 1 give you +2 overall since they're stuck together. So that's just kind of how mercury comes. So oddly, again, like I said, the kind of the one with the most 2's is going to be mercury 1, while the one with only 1 2 will be mercury 2. How do you know it's mercury 1 versus mercury 2? If you see it in a formula, typically speaking, the 2 on the bottom kind of still hangs out. So for example, you got something like this versus something like this. This is mercury 1 oxide, as you have that 2 on the bottom. Here, no 2 on the bottom, and that's -2 +2. This is actually mercury 2 oxide. So that 2 on the bottom here tends to still hang out in the formula, and that's how you could sort of recognize that it is the 1 versus the 2. If you don't see it, then it's probably the 2 +2 charge or mercury 2. Any questions on that there? All right, so why don't you try a couple here? Oh, I just add, we'll do PbO2 there as well. Why don't you also give the formula for the following? Let's do iron 2 nitride. Let's do chromium 4 sulfide. And let's do tin 2 bromide. All right, so names on the left there, formulas on the right. See what you come up with. All right, let's take a look, see how we're doing. So I'll start here on the left. We got CO, which is cobalt, which is a metal, and Cl, which is a non-metal. So again, that checks off the ionic box. Whenever a metal's involved, that's where we want to look. And cobalt is a transition metal, and that's going to check off the type 2 box. That means we do need to figure out, again, the charge on it. So we have 1 cobalt, and if it helps you out, you could just draw out the other things. There's 1, 2, and 3 of these chlorides. That's going to give you a -3. That means here my cobalt is going with a +3 charge, and that's all I need here. So this would be cobalt, again, Roman numeral 3 for the charge. And again, it doesn't matter how many you got, it's going to just be chloride at the end there. Any questions on that one there? Coming down here, Cu is copper, metal. I is iodine, non-metal, so ionic. Always looking at the metal when it's involved. That is a type 2 metal, number 29 there on the periodic table in the transition metal region. Again, in this case, I have just 1 copper. I have 1 iodide, which is group 7, and a -1. That means in this case, we got a +1 happening here for our copper. And again, that is all we need. So copper, Roman numeral 1, because of the charge, and iodide in this case. Coming to our bottom one here, SN is tin, which is a metal. Br is bromine, which is a nonmetal, so that's ionic. Tin is what we want to look at. Tin, again, is not a transition metal, but it is one of those guys just to the right of it, underneath the staircase, that also has a variable charge. So it does fall under the type 2 sort of category in this case. Same deal. We got one tin. It's got a positive charge. And Br is group 7 -1, and there's not just one of them, but there are 4 of them. And again, that gives you a -4 to balance that out. That's going to be a +4 in this case. And that will be 10 Roman numeral 4 for the charge. And we will go with bromide in that case there. Any question on those 3? Coming to look over here, same deal. We got Pb, which is lead, which is a metal. Oxygen is a nonmetal, so that's going to be ionic. Lead, again, much like tin, in the same sort of area on the periodic table. Not really a transition metal, but again, named the same way, has a variable charge. So we do have one lead here. Oxygen is a -2, group 6, and there are 2 of them, and that does give you a -4. The lead here is actually +4, not 2. And sometimes people get 2 by just blindly doing the crossover move, and you will get it wrong in this case. This is lead Roman numeral 4 oxide in this case. So again, as we talked about last time, a lot of times people are taught just to kind of move the charge down or the subscript up. And again, it doesn't work in all cases. About 93, 94% of the time it will work. So if you're good with that, just do it without thinking. But you will not get them all right for sure. Yeah. Any questions on any of those names here? All right, rolling from our name to our formula. First off, I see a Roman numeral, I see a metal, and nitride is a non-metal, so I know it's ionic. So remember, we just really want the basic ions of everybody here and then put them together to equal 0. Nothing much to figure out here because iron 2 means I do have an iron with a +2 charge. That's essentially what that Roman numeral means. I don't have to figure it out. Nitride is nitrogen, which is group 5 on the periodic table. It's got a -3 charge. So we got a 2 and a 3. So basically we need to get everybody to 6 to balance it out. And again, we would need not 1, not 2, but 3 of those irons and 2 of those nitrogens there. And that would give us 3 irons, 1, 2, 3, and 1 and 2 nitrogens. And that would give us our proper formula in this case. Any questions on that one there? Chromium Roman numeral 4 means my chromium's got a +4. And sulfide is sulfur on the periodic table, which is group number 6. It's got a -2 charge. So when we put this together, 4 is what we're looking for. So we will actually need more of the sulfide there to do that. So we just need 1 of those guys, and we need 1 and 2 of those guys. And then we will have our proper formula there. And lastly here, tin, which is SN, will have a +2 charge in this case. Bromide is bromine, which is group 7, has a -1 charge. Again here, we're going to put it together to equal 0. In this case, we do need 1 more of the Br minuses, and that gives us 1 tin and 1 and 2 of our Br minuses. Any questions on any of those names or formulas there? All right, so that is type 2. Again, both of these are ionic compounds, type 1, type 2. Really, the main difference is the metal, whether or not really the decision is, do you need a Roman numeral or don't need a Roman numeral? Basically, it's your decision. And that's usually the decision you have to make when a metal is involved, is Roman numeral basically or no Roman numeral. The next thing we're going to talk about is polyatomic ions. And polyatomic ions are groups of nonmetals that are together, and they do have a charge, and they do have special names. So for example, we'll look at NH4NO3. This is actually a combination of 2 polyatomic ions. If we split this right about there, we have this guy here, which is NH4 plus. That one nitrogen and 4 hydrogens all move around as a whole unit, and it has a +1 charge. And over here is another polyatomic ion. That's a nitrogen and 3 oxygens with a -1 charge. That one nitrogen and 3 oxygens stay together. They never break apart because these things are actually sharing electrons. And we drew some of these when we were doing bonding in the last chapter or so. This guy we drew, and it looks like this. They are sharing electrons, has a +1 charge. This guy here, a little one of our resonance structures, has a -1 charge. Ultimately, this is an ionic compound, so ultimately we're taking +1 and -1 and putting them together. That is why our formula is basically just one of each of these things in this situation. That is also, again, why it doesn't break apart into individual elements or anything like that. They move around as whole units. Again, just based on how they are bonded together and who they're bonded together, they will have an overall unequal distribution of electrons and sort of have either a positive charge or a negative charge. This guy right here is the ammonium ion, not to be confused with ammonia, which is NH3. It has no charge. This guy right here is the nitrate ion. The good news about polyatomic ions are, frankly, you just use the names. Doesn't matter how many you have of them. You just basically use the name of everybody. So when we put those together, we use ammonium and nitrate in this case. So this would be ammonium nitrate. And again, doesn't matter if you have more or one of them. There are not a heck of a lot of positive polyatomic ions. I would say most polyatomic ions are actually negatively charged. And there are a few. This is one, H3O plus is one, and there's a couple others. But most of your polyatomic ions are actually going to be, in most cases, hooked up with a metal. And that's because most of them are negative, so they'll just hook up with a metal. So, and then probably 98% of the time, you're going to have a metal and a polyatomic ion together. And the good news is here, we really just kind of fall back to either our type 1 or type 2 rule. And basically, the decision is, do you need a Roman numeral or not, basically, based off of that. The polyatomic ion doesn't really matter because you're just going to use the name of it regardless of how many you have. So, for example, if I did NaNO3, again, this would break right about there. That is sodium with a +1 charge. That is nitrate with a -1 charge. And again, this is a metal and a polyatomic ion. Again, as I mentioned before, metals are always the most important thing. So I don't care about anybody else but the metal here. And that metal is a type 1 metal, which means I do not need a Roman numeral. And I would just name it like I did a type 1 compound. I would just use the whole name of the metal. And in this case, the whole name of the polyatomic ion. So that would be sodium nitrate. Now, if I took my iron like we saw earlier, and I do the same kind of setup here, and I break it right apart there, I again have a metal and a polyatomic ion. My metal, again, is the most important thing there, and that is a type 2 metal. So that is iron, which is a type 2 metal, which means I'm not really sure what the charge is, but I will know that nitrate has a -1 charge, and there's not one of them, but there's actually two of them in this case, which gives us a -2 charge. That means the iron right here is carrying a +2 charge. And we basically just go about naming this our type 2 way. And I'm going to just erase something and have a little bit of room there to write it. I'll go right there. And if we were going to name this, again, this would be iron Roman numeral 2 because of the charge. And it doesn't matter, we got multiples there. It is still just nitrate at the end, just the whole name of the polyatomic ion. Doesn't matter, again, if you have more than one or just one or two or three or 144. You basically just use the name of the polyatomic ion by itself. Question on that there. By the way, in this formula that I wrote, why did I not just write the formula like this? What does that imply? I have how many oxygens in this case? 32, which seems like a lot, perhaps not what I want, right? So whenever you have more than one polyatomic ion, you always need to put parentheses around the polyatomic ion and the number on the bottom to indicate that you have, for example, 2 of these units. And clearly we didn't have 32 oxygens and 1 nitrogen in that particular case. Any questions on that there? Here is, good talk, let's go back. Here is a list of some polyatomic ions, and you do need to know them, but when we look at these lists, there are ways you could kind of group things together to make it easier to sort of know. Again, you can see ammonium up there is our one kind of positive guy, but there are a couple others. When you look at these polyatomic ions, for example, SO4 2 minus, that is 1 sulfur and 4 oxygen with a -2 charge. That is the sulfate ion. If you look at SO3 2 minus, that is 1 sulfur and 3 oxygens with a -2 charge. That is the sulfite ion. If you look at NO3 minus like we just did, that is our nitrate ion. NO2 minus, that is our nitrite ion. So in a group of 2, for example, that are related to each other, the only difference, for example, between these 2 guys is actually just the number of oxygens. Everything else is the same, has the same charge, has the same number of sulfurs, everything's the same. And really the only difference between these 2 guys is the number of oxygens there. They all have a -1 charge. They all still have a nitrogen. So in a grouping of 2 or more, the one with the most oxygens usually will end in 8. So 8 is the one with the most oxygens. And the one with the least number of oxygens will end in ite. And that's a good way to sort of memorize these guys. So for example, if you want to know all the ites and memorize the ites, all you have to do if you want an 8 is just add an oxygen, everything else stays the same. Or vice versa, if you want to know all the 8s, you need an ite, you just take off an oxygen, everything else stays the same, the charge and everything like that. That's a really good way to kind of group them together. If you don't want to kind of group everybody individually, just learn either the ites or the 8s and know how to adjust it to the other one by either adding an oxygen, taking an oxygen away. There's also groupings of 4 that are related to each other, like, we'll go here, ClO4 minus, ClO3 minus, ClO2 minus, ClO minus. And all these guys have a -1 charge. The only difference, again, between all these is the number of oxygens. So in a grouping of 4, you can kind of break it up by 2s. And the ones on the right-hand side here have the least number of oxygens out of those 4. So we know that they should end in ite, right? So that is chlorite. We know that this guy here will definitely be chlorite. And clearly we cannot have the same name for 2 different things. So in a grouping of 4, the one with the least number of oxygens, in addition to ending in ite, we'll start with hypo. So that is hypochlorite and chlorite. We go to the left there, kind of the same idea. This would be chlorate because that's the most oxygens. This would also be chlorate. Once again, we cannot, like before, have the same name for 2 different things. So in a grouping of 4 where the one with the most oxygens will have a per in front of it. So that is perchlorate, chlorate, chlorite, and hypochlorite. By the way, if I switch out the chlorine, which is a halogen, and I did not ClO3 minus, but did BrO3 minus, instead of chlorate, that would be bromate, yeah? If I swap it out for an I, instead of bromate, it now becomes iodate. Yeah, so you can actually swap out the halogen in any of those four, and basically it's named the same way. Just use the halogen name to start with it. And again, this is sort of what we're talking about, sort of ways to adjust it is a really good way. Let's just say, for example, I wanted persulfate and hyposulfite. What would those be, you think, based on these? What would persulfate be, you think? Well, this is chlorate, and that is perchlorate. That is sulfate, so persulfate should have more oxygens or less? More, yeah. So you just pop an extra oxygen on there. Everything else stays the same, right? There it is. And this is sulfite, right? That is chlorite, and that is hypochlorite. So hyposulfite would have SO2, 2 minus, yeah? So again, if you kind of know how to adjust them, you know, it makes life maybe a little bit easier. I'll just throw it over there as well. So again, if you just kind of know grouping of them, the eights, the ites, and okay, well, I'm at ite and I got to go to per. I got to add a couple of oxygens to that guy, right? Or I'm at 8 and I got to go down to hypo. I got to drop off a couple, right? And you can kind of adjust. Or if I just need to go from 8 to ite, I just drop off of one oxygen. So, you know, that's a really good way to sort of think about how to have these in your head and understand it. Other things that we sometimes will see on here is sometimes we will put, for example, that is carbonate. Now, sometimes we may put an H plus on something and we get HCO3 minus. We put an H on here, but the +1 and -2 leaves us still a -1 charge overall. And basically, we just put a hydrogen in front of it. So this is what is known as hydrogen carbonate. Now, hydrogen carbonate is still historically called bicarbonate. And sometimes people will use the bi instead of the hydrogen, and that's still used today. We also see that with sulfate and hydrogen sulfate as well. That is sometimes referred to as bisulfate. Where is it? It should be up here somewhere, I think. There's hydrogen carbonate, and there's our bisulfate. Again, similar type of idea. So if you put a hydrogen on something, it's basically hydrogen, whatever you put it on. The charge adjusts by 1 because you're putting on an H plus. Now, in addition to that, there are some that end in IDE. So there are some polyatomic ions like cyanide, hydroxide, wherever it is right there, and some other ones there that do end in IDE, azide, that's peroxide, ends up in IDE. So you can remember those as well. They're very commonly coming up along the way. And again, here's phosphite and phosphate. And obviously, if I want perphosphate, we would just add one more oxygen and so forth, and hypo if we go down that way. Any questions on that there? So why don't we try some? Let's do, we'll get rid of this, so we'll have the chart up here. All right. So we'll do, let's do, what are the names of the following? Let's go with CaOH2. Let's go with SnClO3,4. Let's go with and then why don't you write some formulas for, let's do copper 2 permanganate. Let's do let's do iron 3 bicarbonate. All right, so some names and then some formulas there. Okay, let's take a look. So we see calcium and we see hydroxide. And remember, the metal is kind of the important thing here. So that metal is group 2, which is a type 1, which means I don't really have to figure out anything in terms of Roman numerals or anything like that. So I really could just go right into naming, which is calcium. Again, we're just going to use the whole name of the metal. And remember our polyatomic ion here, we're going to go with just the name of it, which is hydroxide. So this would be calcium hydroxide in this case. Taking a look at this one, that is tin, which is a metal. That is chlorate, which is a polyatomic ion. Once again, the metal is going to dominate here whenever it's involved, and that is a metal that does need a Roman numeral. It says a type 2 metal. So again, here we have one of those tins. The ClO3 is -1, and we have 4 of them. So again, if you want, you could draw them out to help you. That's a -4 charge. That means that the tin here is going to be carrying a +4 charge to balance it out. And that means that this would be tin Roman numeral 4, again, for the charge. And again, it doesn't matter how many of those polyatomic ions we got. We're just going to use the name of it. So that would be tin Roman numeral 4 chlorate in this case. Any questions on those there? This is lithium, which is a metal. HCO3 minus is bicarbonate or hydrogen carbonate, which is a polyatomic ion. Once again, with the metal being involved, that's where we want to kind of focus our attention to. And that is a type 1 metal. It's its group number 1, which means in this case, we don't really need to figure out much other than name it. So that's going to be lithium. And it is your choice. This is hydrogen carbonate. Or lithium bicarbonate is fine as well in this particular case. Any questions on any of those names there? All right, so rolling to our name, we want some formulas. I see copper, Roman numeral 2, and permanganate. Again, this is going to be an ionic type of situation. Copper Roman numeral 2 means I do have a copper with a +2. Permanganate is a polyatomic ion, which is MnO4 minus. Again, that entire thing has a -1 charge, which means when I put it together, I need not one, but I actually need 2 of them to balance it out. And that would get me Cu, and because I have more than one of those polyatomic ions, I do need to put parentheses around it and a little number there on the bottom. Any questions on that one there? Lastly here, we got iron Roman numeral 2, which is a iron with a +3 charge because of the Roman numeral. Carbonate is CO3 2 minus. So again, we're really putting together a +3 and a -2. And again, the common number there is 6. So we just want to get everybody to 6. And to get iron to 6, we need not one, but 2 of them. To get our carbonate to 6, we actually need 3 of them. So that's going to give us our formula. We have iron, 2 of them, 1 and 2, and carbonate 1, 2, and 3. Because this is a polyatomic ion, we do need our parentheses one more time. So we're not doing like 32 of them, and maybe put the right number on the bottom there would help as well. CO3 with a 3 on the outside in this case. Any questions on any of those there? So really, polyatomic ions for the most part is going to fall back to type 1 or type 2. And again, the decision there is Roman numeral or no Roman numeral. Now, earlier I talked about the idea of obviously you see no prefixes here, but this would be the one and probably only place where you could have a metal and also a prefix in the name. And that is because you didn't really put the prefix in. But for example, the polyatomic ion itself has a prefix like dihydrogen or something like here. So that would be the only case where you would see really a metal and a prefix together, but it's not really a true prefix. It's just part of the polyatomic ion's name. And other than that, you should never really have a prefix and a metal together. All right. So think I'm going to do this. We're going to go type 3 compounds, speaking of prefixes. And type 3 compounds are different. They are covalently bonded together. They're sharing electrons. And speaking of prefixes, this is the place where prefixes are used. So we do use prefixes here with type 3. We use, for example, mono, which means 1, di, which means 2, tri is 3, tetra is 4, penta is 5, hexa is 6, hepta is 7, octa is 8, maybe nona is 9, and maybe a deca, why not, for good measure, it's 10. So these are the prefixes that we use. The really good news about type 3 is it's really the easiest ones to name, but it is also the ones people screw up the most on because they want to do all kinds of weird things with it. So the deal here is we're covalently bonding, we're sharing electrons, we don't have ions. So we don't have to worry about figuring out what is the charge on or anything like that. Frankly, all you have to do in this case is pick the right prefix for how many of each of those elements you have. So the way that we name it is we go prefix if necessary, if needed, and the whole name of the first element. Then we go prefix on the second name, and the second name is named like we've been doing. It's the nonmetal name with the IDE at the end. So prefix on the first one if you need it, whole name of the first element in the formula, and then prefix on the second one, IDE ending like we've been doing for our nonmetals, basically. So why do I say prefix on the first one? Well, there are a couple of important rules. The first rule is no mono on the first name, but it is okay on the second. Yeah. The second thing that commonly happens in type 3 naming is you oftentimes will get a couple of vowels that will back up to each other. So you'll maybe have an O from the prefix and an O from the element, or an A from the prefix and an O from the element name. In this situation, we typically get rid of the prefix vowel and kind of take it out of the name. 2 I's in a row are actually okay, but like an OO and an A and an O is not so good. An example of maybe all these things together, we take our friend here, CO, right? So the first thing when we see capital C, capital O, carbon is a nonmetal, oxygen is a nonmetal. So that tells me it is a type 3 sort of compound. And because it's a type 3 compound, I really don't have to worry about naming anything or anything like that. Just got to pick the right prefix. Nothing written there means 1, so I have a mono prefix for this guy. Nothing written there means 1. I have a mono prefix for that one. Again, here we are not going to use mono on the first name, so we'll go with just the whole name of the first name. We can use mono on the second name, and our second element ends with the IDE, but we do not call this usually carbon monoxide, right? We call it carbon monoxide, and that is because we dropped the O off of the prefix, and this is carbon monoxide, in this particular case. So again, mono okay on the second, not on the first, and then if you got an OO or an AO, drop the vowel off of the prefix is typically what happens in this case. Any questions on that there? All right. So as I mentioned, that's what we just talked about there. And here again is our prefixes. And usually it's that A or O that gets sort of dropped along the way. Now, a couple of other types of considerations for type 3 naming. As you can see there, instead of tetraoxide, we're going to drop the A off of it. And instead of mono, like we just did there, we're going to have monoxide. Now, there are certain compounds that are just named by common names. And H2O is water. Yeah, it is not a trick question when you see it. Just put water and move on with your life. It is not dihydrogen monoxide because nobody wants a refreshing glass of dihydrogen monoxide, right? So don't do that. I like all the funny names I get, but it's just water. NH3, as we talked about a little bit earlier, is ammonia. Again, has no charge and one less hydrogen than ammonium with the +1 charge. That's a polyatomic ion. And CH4 is methane. That is the simplest organic molecule you could have. So those guys should definitely go by common name. In addition, hydrogen, as we talked about, I think maybe last time, hydrogen itself, when it's attached to another nonmetal, is really more treated like a type 1 compound than a type 3 compound. So if you had HCl, which is in the gas phase, this would be called hydrogen chloride. And again, it wouldn't be hydrogen monochloride or anything like that. We just call it hydrogen chloride. It really is named more like a type 1 compound than a type 3 compound. Even if you had H2S, which is a gas, this would be hydrogen sulfide. So even when you have multiples of the hydrogen in this case, is still called hydrogen sulfide gas, deadly toxic gas that you don't want to inhale as well. So hydrogen, even though technically it's a nonmetal, has a lot of characteristics, especially since a lot of these guys can become acids. They're more named like type 1 compounds when you have hydrogen sort of in front like that. Any questions on that there? All right, so why don't you name those and give some formulas here. Let's do dinitrogen pent. Pentoxide. Let's do carbon hexabromide. Let's do one that probably doesn't exist, dioxygen. Heptasulfide. Why not? All right, let's take a look at these. These, again, really should be probably the quickest ones you do. There's not much to figure out other than sort of pick the right prefix. So I see I and O, which is 2 nonmetals, so that checks off the type 3 box. I just need to figure out what prefixes I want. So 2 is di, 7 is hepta, and now we just need to put it together correctly. So diiodine, again, we're going to use the whole name of the first one. The second one we'll use our prefix and the IDE version here. Here we are going to drop the A off of the prefix as we have an A and an O. That would back up, obviously, if you just kind of put it together. So diiodine heptoxide. Once again, here I see carbon and oxygen, which are 2 nonmetals, tells me it's type 2. Here, we only have 1 carbon, that is mono, but we do not use it on the first name, so we don't have to worry about that. Di here is our second one, so just the whole name of our first element, and dioxide there for our second there. Lastly here, we have phosphorus, which is a nonmetal, chlorine, which is nonmetal. Once again, we have only 1 phosphorus, which is mono. Again, not going to use on the first one. We have tri here for 3. So this would be phosphorus trichloride. Any questions on any of those names there? Coming to this one, which I think is probably even quicker than any one you do. As soon as you see prefixes, you should be happy. Always just write what it says. Di is 2, nitrogen is N, so you just write that. Penta is 5, oxygen is O, so you just write that. Again, there's no charges or anything to balance. You're basically just writing what it says. Carbon with no prefix, but we do see a prefix here, which is hexa. Carbon and bromine is 2 nonmetals. So I know with no prefix, that is one of those. And hexa is 6 and Br. And we just go like so. Lastly, here we have di and hepta, which are 2 prefixes. And this is the only place where prefixes can happen. So di is 2, oxygen is O. Hepta is 7, and sulfur is that, whatever that may be as well. Yeah. Any questions on any of those there? Type 3. All right. So going back, I think the last thing we're going to talk about is, I feel like I passed it here. There it is. There it is. We're talking about how we name acids, and acids are substances that are able to produce H plus ions in solution. H plus is the obviously the hydrogen ion. It is also sometimes in acid-base chemistry referred to as H3O plus, which is the hydronium ion, which actually is a polyatomic ion. And they basically mean the same thing. They basically mean the acid part of the solution. Now, if it is a solution, that is an aqueous environment, which is AQ, means aqueous or water environment. And typically acids are obviously an aqueous solution. So what makes something an acid is that ability basically to produce free floating around H pluses in solution. So the ability just basically to release some H pluses into that solution makes something an acid. So acids are essentially ionic compounds, and the cation for all acids is H plus. So H plus is the cation for all acids. The anion is obviously will need to be balanced that out to 0. Now, when we name acids, it's all about oxygen and whether or not the acid has oxygen or not. If the answer is no oxygen, your acid will start with hydro something ic acid. So again, if you see an acid and it does not contain oxygen, we'll start with hydro, it will end with ic acid. The middle part here is actually the negative anion. It's the negative guy, is the middle missing part. So for example, if we take HCl in the aqueous environment, that makes it, by the way, an acid. There is no oxygen in there. So this would be hydrochloric acid, the chloric part for the chlorine that is there. You had HBr. Again, no oxygen in there, so that will be hydrobromic acid. Again, the bromine part is the missing part there in this particular formula. That again is what makes, for example, HCl here in the aqueous form different than HCl in the gas form. HCl in the gas form is hydrogen chloride gas. You actually take hydrogen chloride gas, you bubble it through water, you get hydrochloric acid, basically there. And that's what in a water environment. So typically speaking, when we write formulas for acids, they typically will have an AQ or aqueous symbol next to them to indicate that they're in a solution and that they are basically an acid in that case. Now, what happens if your acid does have oxygen? So if the answer is yes to oxygen, if your acid does have oxygen, it will contain typically a polyatomic ion. And as we just talked about, our polyatomic ions end in one of two ways, either ate or ite. So if your acid does have oxygen and your polyatomic ion ends in ate, your acid name will be something ic acid, like HNO3 also gets the aqueous symbol. NO3 is NO3 minus, which is nitrate. By the way, the cation here is H plus. The anion is NO3 minus in this case. Because this ends in ate, this guy here is nitric acid. Yeah. If you have H2SO4, also in the aqueous symbol, that is sulfate, SO4 2 minus. By the way, that is why we have not one hydrogen in this case, but we have two of them, right? To balance out the -2 charge from sulfate. Again, it's like an ionic compound, it got to equal 0. So sometimes you'll have one hydrogen in an acid, sometimes you may have two, sometimes you may have three, depending if it's diprotic, polyprotic type acid. But you do need to balance it out to 0. So once again, this ends in ATE sulfate. This here would then be sulfuric acid, yeah. So again, if it ends in ATE, IC, you can remember it like you ate too much, you feel icky. Yeah, that's a good way to remember that, perhaps, or not. I don't know, your choice. So if your oxygen in your acid, it has 8, that is how it ends. If it is yes to oxygen, and your acid and your polyatomic ion ends in ITE, your acid name will be something OUS acid. So if I take HNO2, NO2 is really NO2 minus, which is not sul, which is nitrite. And that would mean that this acid would be nitrous acid. If I take H2SO3, SO3 is SO3 2 minus. That is sulfite. That means that this would be sulfurous acid. Again, here we have two hydrogens to balance out the -2 charge of our sulfite in this case. Nothing has hydro if it has oxygen. So if it has oxygen, you put hydro on it, it is incorrect, yeah? So hydro is only for acids that do not have oxygen, yeah? So you don't ever want to kind of mix hydro in with everything because it sounds more chemistry-like or anything like that, put hydro on everything. Question on acids. Good news is bases are named like normal because a lot of strong ones contain hydroxides, so they're just like sodium hydroxide, potassium hydroxide, they're just kind of named like you would name a polyatomic ion, basically, in this case. All right, any questions on acids there? So I think that might be it. I think we're out of naming at this point here, I think. We'll take a look at a couple here, just finish up on. So let's do all right, so why don't you write the names and the formulas for each of these, and we'll talk about them here, finish up on.